All right, so today we're going to talk about rational functions and their graphs, the graphs of rational functions. We're going to transform rational functions by changing parameters. You guys may or may not have heard of the name of a rational function, what the graph looks like. You know how for quadratic functions we have parabolas. For a rational function, the graph is called a hyperbola. So not hyperbole, it's very close to that, but it is a hyperbola. Okay, we're going to talk about the parent function first. So the parent function for rational functions is y equals 1 over x. This is the most basic rational function. And you can see the points from this graph, but you can also generate some points just from plugging in values for x. Okay, on this graph here, we can see if we plug in 1, if I plug in 1 for x, y would be what? 1, because 1 divided by 1 is 1. Okay, if I plug in 2, 1 over 2, yeah, 1/2. Okay, if I plug in 1/2, what's 1 divided by 1/2? 2. Because really, if you have 1 over something, isn't it just the reciprocal? So the reciprocal of 1/2 is 2. Now, just like with the inverse function, remember how we were talking about inverse variation? Wasn't this the form? Okay, the negatives are going to create the other branch. So if you plug in -1, you have -1. -2 would be -1/2, -1/2, -2. Okay, so these are just some points that we can use when we're graphing. We can graph the parent function and then use the transformations to adjust the graph. So again, there's some review stuff from first semester in here. One thing that you can't see on this graph, which is something that we're going to talk about today, are asymptotes, which are places where they're undefined. With exponential functions, we had an asymptote at x equals 0. If you were to plug in 0, that would be what? It's undefined. So at x equals 0, the graph is undefined, right? Because that would be like 1 over 0, right? Okay, so let's go back here and just refresh ourselves with the transformation rules. Okay, so the value on top is called your A value. So if that A value is not 1, that is going to be a vertical stretch or compression. Okay, that's your value of A. That's your vertical stretch or compression. If the A value is negative, that means it's a reflection. The vertical translation is always added to the outside. So if you have plus K here, that is telling you whether the graph is moving up or down. Again, that's exactly the same thing that we did earlier on. Okay, and then on the bottom, the x minus h, okay, that value of h represents the horizontal translation. Notice that it says you're going left for x is less than 0. You're going right for when h is greater than 0. We always, with our horizontal type of transformations, we have this minus here. Okay, the minus means that you're going to be doing the opposite. This doesn't have the horizontal stretch or compressions in here. If there was one, there would be like a factor here, the 1 over b. That would be the horizontal stretch or compression. But remember, a horizontal stretch is going to have the same effect as a vertical compression. A horizontal compression is going to have the same effect as a vertical stretch. So a lot of times that's why we'll just put it in terms of the vertical stretch or compression. Okay, and then just like with our inverse variation, you have the two branches. Okay, this parent function has to have the two branches in it. Okay, we're going to talk about the asymptotes. We're also going to put them on this graph. You guys remember asymptotes from our exponential function days? And how we wrote them on the graph with a dashed line? So there are two types. There's a vertical and there is a horizontal. So the vertical asymptote is at x equals h. Okay, so x equals h, whatever your value is for h there. The horizontal asymptote is going to be at k. Bless you. Okay, and your y is going to equal your value for k. These are also related to your domain and your range. When we have like this, the x equals h, the y equals k, for our parent function, the h is added or subtracted to x. There's nothing added or subtracted there. There's nothing added or subtracted to the outside. So our horizontal and vertical asymptotes are at x equals 0 and at y equals 0. Okay, again, those are dashed lines for the x and then the y. So you guys add those to your graph. When we do the asymptotes, I'm going to use different markers, so you guys are welcome to do that on your homework. It makes it a lot easier to see where the bounds are for the different functions. Your domain is going to be written in set builder notation. So the rule for your domain is it's going to be all values of x such that x cannot equal your h value, which remember, we just said that is our vertical asymptote. So this will not be able to equal the vertical asymptote. For the domain, when we were working on that, we talked about how when you have fractions, you cannot have the denominator equal 0. So when you have a function, if you look in the denominator, if you had x minus h, okay, whatever you had for that, you would set it equal to 0. And then you would add h to both sides. That's how you would find your final value. That's why x cannot be h. Do you guys remember this notation, your set builder notation? What this means? All real numbers x such that x cannot equal h. Because we're going to be using that notation for this. Okay, and then for your range, it's going to be y such that y cannot equal k, which k is our horizontal asymptote. Okay, so a lot of this has to do with the structure. Just by understanding this setup and what your variables represent, you can find these things without even graphing. We are going to be comparing these to the graphs today. And this says, what are the asymptotes and the domain in the range of your parent function? So really, we already talked about what the asymptotes are. I just want to remind you that whenever you're writing an asymptote, remember, an asymptote is a line. So when you're identifying what the vertical asymptote is, it's x equals 0, not just 0. The horizontal is going to be y equals 0. Okay, so all of your asymptotes are equations of lines. Okay, and that's why I would mark it off if I asked you for an asymptote and you just put 0, because that doesn't tell me what line it is. Vertical is always going to be with x, horizontal will always be with y. All right, so then for our domain, it's going to be all the values of x such that x cannot equal the vertical asymptote. And the range is going to be related to the y. Okay, which is your horizontal asymptote. And the reason why I'm labeling these is because in this case they're both the same. So I want you to know which produces which here. All right, so for our first example, we are going to use the graph of f of x equals 1 over x as our guide. We're going to describe the transformation, and then we're going to graph the function g of x equals 1 over x plus 2. All right, if the format is x minus h, we could write this as g of x equals 1 over x minus negative 2. Then you can see what your h value is. Okay, so our h is negative 2, which means if that value is negative, you are going to have a horizontal translation to the left. So you're going to have to write that out, that it's a horizontal translation, 2 units left, because they're asking you to describe the transformation in the directions. Now there are different ways that you can graph this. You could plug in values for x and then find the output. I'm going to just show you how you can use the original function as your guide and go from there. So remember, if we're using f of x equals 1 over x, didn't we already come up with a bunch of points for that when we wrote them down up here? So our points were, we did 1, 1, we did 2, 1/2, we did 1/2, 2. Because this graph is going out to 5, I might want to do like a plug in 4. If you plug in 4 for x, what would your output be? 1/4. And then if you plugged in 1/4, your output would be 4. And then we're going to do the same thing with the negatives. So negative 1, negative 1, negative 2, negative 1/2, negative 1/2, negative 2, negative 4, negative 1/4. Okay, that way we get the 2 branches. And then remember, for g of x, all we have to do is move all of these points 2 units to the left. Okay, we should also think about what our asymptotes are going to be. So for the vertical asymptote, that's going to be x equals h. Remember, our h value is -2. So x is going to equal -2. The k value will be added to the outside of the function. Okay, so what that would look like if you had a k value that wasn't 0 is something like this. We don't have anything added on the outside, which means the horizontal asymptote is just y equals 0. So if you graph the line x equals -2, which I'm going to do that first. Remember, it's a dashed line. So this is a vertical line. X equals -2, and then y equals 0. Okay, now I am ready to graph this part. So I am going to first go to 1, 1. Okay, so at 1, 1, I just have to transform this 2 units to the left. So don't put a point there. That's the parent function, right? So we're going to go left, 1, 2. Now I'm going to go to 2, 1/2, and I'm going to go left, 1, 2. I'm going to go to 1/2, 2. I'm going to go left, 1, 2. I'm going to go to 4, 1/4, 1, 2. And then 1/4, 4, 1, 2. And then you're connecting these with a curve. This is going to follow both of those asymptotes. And then I can do the same thing here. So I'm at -1, -1, and then I go to the left 2, -2, 1/2, 1, 2, -1/2, -2, 1, 2, -4, 1/4, -1/4, 1, 2, so that one's a little off there. And -1/4, -4, 1, 2. Alright, now I'm just going to show you on Desmos. So you could do this part with me, the Desmos.com. Right, you can just go to start graphing. And you can put y equals, or you can put f of x equals. And for that one, we had 1/x plus 2. So you can do 1 slash, and it will change it into a fraction, x plus 2. Oops. There you go. And then look, you can see that this line is getting closer and closer to your -2 over time. This is getting closer and closer to 0. It's nice because you can kind of zoom out and you can see, or you can zoom in and you can see what it's getting closer and closer to. Alright, so for example 2, we are identifying the asymptotes, the domain and the range of the function. So you don't need the graph to do this. You can just use the equivalent form. But we are going to look at it to check our work. Okay, so remember, with the asymptotes, the x equals h, the y is going to equal your k value. Okay, so let's see if we can come up with what our h is and what our k is for this example. Okay, so with your elbow partner, will you guys identify your h and k for part A and for part B? Okay, so Joe, what did you and Macy agree was your H? Good. Okay, and then Ria, what did you say your K value was? Good. All right, so then for your asymptotes, if your vertical is x equals h, it'll be x equals -3, and then y is going to equal -2. Okay, for the domain, it's all values of x such that x cannot be h, which really, again, if you think about this, in the denominator, we know that x plus 3 cannot be 0. So x cannot be -3, which is the value for h. Okay, for the range, y would not be able to be -2. Okay, so see if you can do that for part B. And then we're going to look at the graph. You can even graph that on your graphing calculator, or if you want to pull up Desmos and graph it on there, that would be great. Okay, and then let's check to make sure you guys have that correctly. So x such that x cannot be 6, y such that y cannot be 0. And then let's look and see how our graphs are going to look in relation. Okay, so if I have 1 over x plus 3 minus 2, okay, you can look and you can see this is getting closer and closer to -3. And then see how this one moved down? You can also graph your parent function so you can see what happens in relation. So the blue is I graphed the parent function in blue, and then our part A in red, so you can see this is being moved down 2 units, and then it's being moved to the, where is it, horizontally? Where is it being moved horizontally? 3 to the left. Okay, so 2 down. But that can help you pick out where it's approaching. Okay, so it's getting closer and closer to -3 on the x-axis. Okay, and it's getting closer and closer to -2 on the y. The second one, your value at 1 over x minus 6. Now you can see here the x is getting closer and closer to 6, but it's still approaching our axis here, our x-axis. Alright, let's flip it to the back. So there are some different rules that we have for finding zeros and asymptotes in a rational function. So first it says if your function is p of x over q of x. So those are both going to be different polynomials. Okay, your p of x is going to be the numerator. Okay, so when I say p of x, it's the numerator. When we say q of x, that's the denominator. And there are certain rules that we can use. So the first one is for finding zeros. What's another name for zeros? Yep, x-intercepts and and roots. Okay, good. So if you are finding zeros, all you're doing is finding the x-intercepts or the roots. Do you guys remember back to your Algebra 1 days how you would find the x-intercept? Or even how you'd find the y-intercept, no matter what the function looked like? Okay, so if you wanted to find the x-intercept, what would you plug in for, what would you substitute 0 in for? Your y, okay? So basically what happens if you have a rational function, so let's just say we have like 1 over x, okay, equals y. If I wanted to, let's say we have this actually. Y equals x plus 1 over x plus 2. Let's say I want to find out where the x-intercepts are. Can't put that away. If you plugged in 0, how would you solve this for x? Yeah.
You would multiply both sides by x plus 2.
Good. Multiply both sides by the denominator so that they cancel, right? Now, because this is 0, when I multiply it, what do I get? 0. So really, isn't that always going to happen if this is 0 for y? So it's like you're setting 0 equal to what part of this? The numerator. So that's our rule. To find the zeros, you're going to set p of x equal to 0, which remember p of x is our numerator. And then you're going to solve for your variable. Okay, so in most cases that will be x. Okay, if you were finding the y-intercept, you would just plug in 0 for x, and if there are multiple x's, you would plug in 0 for both of them. To find the vertical asymptotes, the vertical asymptotes, remember, are related to the domain. And with the domain, if you have a fraction, what don't we want? Yeah, we don't want the denominator to be 0. So for the vertical asymptotes, what you do is you set q of x, or the denominator, equal to 0, and solve for x. Okay, so again, the vertical, now we're using the denominator because that is tied to our domain. The horizontal asymptotes have a set of rules that are all based on the degrees. So if you notice here, it says if the degree of p is greater than the degree of q. If the degree of p is less than the degree of q. If the degree of p is equal to the degree of q. So it's all about finding the degrees of the numerator and the denominator. Kira, how would you tell somebody how to find the degree of a polynomial?
It's the exponent.
Yep, the what exponent?
The biggest one.
Yep. Okay, so remember the degree is going to be the highest exponent. So that's what we're going to do for these. We're going to find the degree of the numerator and the degree of the denominator and then compare them. Okay, so when you're comparing the degrees, I'm going to write just some shorthand over here. Okay, if the degree of the numerator is greater than the denominator, what that means is there is no horizontal asymptote. Okay, so that would be the degree. I'm just going to write the numerator greater than the denominator because I think that's easier to remember than your P and your Q. If the degree of the numerator is less than the degree of the denominator, then your asymptote is going to be y equals 0. So that's if the degree of the top is less than the degree of the polynomial in the bottom. And then the last one is for when they're equal. When they're equal, you actually create the asymptote by putting the leading coefficient of the numerator over the leading coefficient of the denominator. I'm actually going to show you what that looks like. Okay, so if you had something like your function was f of x equals, and you had 2x plus 1 over 3x minus 5. Okay? Chris, what's the degree of the numerator here?
1.
Yep. And what's the degree of the denominator, everybody? 1. Okay, so if the degrees are equal, what's the leading coefficient of the numerator? 2. What's the leading coefficient of the denominator? 3. So then this would be your asymptote, 2/3. Y equals 2/3. Okay, so then when you looked at your graph, you would see it would get closer and closer to the value of 2/3. And we are going to do some graphing now in example 3. So in example 3 it says identify the zeros and the asymptotes of each function, and then we're going to graph it. You do need to put the asymptotes on your graph, so make sure that you do that. For the first one, we have f of x equals x squared minus 3x minus 4, that's divided by x. B is f of x equals x minus 2 over x squared minus 1. So the first thing that you want to do, if you can, is factor. Okay, so if possible, you're going to factor. So in this one, we can factor. So on the top, I'd start with x and x. Has to multiply to -4, but add to -3. So that's going to make our steps a little bit easier. So remember, the first thing that we're going to do is find the zeros. So to find the zeros, that's when you're going to set the numerator equal to 0 and solve. So now that I already have the numerator factored, I can use my zero product property. So x minus 4 equals 0, or x plus 1 equals 0. When you're writing out your zeros, I'm going to have you write them as points so that they're not confused with your asymptotes. So I would have 4, 0, and I'd have -1, 0. All right, and those are both points you can put on your graph right away. So 1, 2, 3, 4, -1, 0, you can absolutely do that. Now we're going to find the vertical asymptotes, which is when you set the denominator equal to 0 and solve. Well, the denominator in this case is just x, so x equals 0. That's going to be your vertical asymptote. Okay, so I'm going to put that on my graph. Again, the asymptote is a dashed line, and then we're going to label that as x equals 0. Okay, for the horizontal asymptote, we're going to use our rules above. Okay, so the degree of n, and then I'm going to compare that to the degree of the denominator. Kelsey, what is our degree of the numerator?
2.
Yes. And Kate, what's our degree of the denominator?
1.
Yep. So what is bigger, 2 or 1? 2. Okay, so we have the numerator is greater than the denominator. So when I go up to my rules, n is greater than d is my first one, which means that there is no horizontal asymptote. Okay, so I only have the vertical asymptote here. So on our graphing calculator, we are going to find some more points because these aren't enough points for me to get a good picture. When you are using your graphing calculator, you do need to make sure that you put the numerator and the denominator in parentheses when there's more than one term. Okay, like the top's a trinomial, so I have to put that in parentheses or else your calculator is going to do the division before any of the subtraction. This is just one term, so that's not necessary to put in parentheses. And here's a good picture of what it looks like. Kind of looks like two baseball seams here. There's lots of different types of hyperbolas. We're going to look at a few different types today, but they're not always the two branches that we saw earlier. Now I'm going to go to my table and get some more good points here. So 1, -6, that looks like a nice point. Okay, at 2 I'm at -3. That'll be good. At 5 I'm at 1.2. So that just gives me a series of points so I know how to curve my line here. And then when I go to the negatives, at -2 I'm at -3. At -4 I'm at -6. Okay, but it will be helpful to know what's happening up here. This point would be between -1 and 0. Do you guys remember how to change that so you can see it? There's a couple different ways. If you just go to second table set, you can start at 0. You can go by halves. So if you go by halves, now you can see, oh, at -1/2, I'm at 4.5. So that's going to, again, just help you get a nice curve on your graph. Okay, so for B and C, I want you to find the zeros, the vertical asymptotes, and the horizontal asymptotes. I'm going to give you some time to do that. And then you are going to want to graph it. Okay, so will you write these down? Your f of x equals x minus 2 over x squared plus 1. And then for C, your f of x equals 4x minus 12 over x minus 1. So at the very least, I want you to do your zeros, your vertical asymptote, your horizontal asymptote. And then we're also going to look at some of those graphs together. check in with your elbow partner. One thing you want to check for is that the zeros are written as points, and then any asymptotes have the y equals. Make sure the asymptotes are in the graph. Make sure you guys have your asymptotes on the graph, the dashed line. Alright, so for your zeros, you should have 2, 0 as your point. Your horizontal asymptote, if you factor the denominator, because this is the difference of two squares, x plus 1 times x minus 1. Okay, that's going to be x equals -1 and x equals 1. Make sure that you have two separate equations here. Okay, you should have two separate. Okay, and then I put horizontal, but that was your vertical, sorry. Vertical, getting ahead of myself. Okay, so then for the horizontal, you're gonna compare the degrees. Okay, so in this case, the degree of the numerator is less than the degree of the denominator, which means your asymptote is going to be what? Yep. So now I'm going to put what I know on there. So I have two vertical asymptotes, one at x equals -1. I'm going to label it in a second. One at x equals 1. And really, when you put all these on there, it looks like a what? H. And it looks like an H. Those are going to show you where your bounds are. So here's x equals -1, x equals 1, y equals 0. All right, we ready to see what this thing looks like? Oh, I also wanted to put on there, so I have 2, 0. Do you guys feel like that's weird?
Yes.
Why? Because your asymptote is there. Now, with rational functions, horizontal asymptotes can be crossed, vertical ones cannot. So the vertical ones cannot be crossed at all, but the horizontal, because those do not have to do with the domain, they actually can be. Sometimes they are and sometimes they're not. So it is strange to have the point on an asymptote. It'll never happen if it's vertical, but in some cases it will happen if it's horizontal. So let's look and see. Let's go to decimals and let's do some investigating. Okay, so y equals x minus 2. See, I have to put this in parentheses, so x minus 2 divided by, and then x squared. Ooh, look what's happening here. Minus 1. Whoa! We have 3 branches here, don't we? Kind of looks like you have a parabola looking thing, a U-shaped thing, and you can. You thought you did the wrong thing when you graphed it?
Yeah.
Okay, so really what you want to do is pick out like a point here. so this one is the 0.3 close to 2, so that would be a good one to pick out. That's gonna be next to, this is your y-intercept, your 0, 2. So we'll focus on that. We already have this point here. Do you guys know why this point automatically popped up on decimals?
Logic.
No.
Because it's a calculator.
No. What's the significance of this point compared to any of the other ones on here? These didn't pop
It's a
up.
3.
It's the what?
A 3.
Why did this point pop up instead of like this one? It's the maximum. Okay, that's the maximum point. That's the highest it's going to reach in this region. It's your local maximum. Okay. That. Now look what happens if I do this. Whoa.
What kind of witchery is this?
That looks a lot
You got
nicer.
it.
I like that one better.
What if I
I see a
do-
person.
What happened to it?
It looks like an hourglass.
What if I do?
Yeah. Wow. Look at that.
That's kind of neat.
What if I start making some trinomials?
Oh,
Make it a 5.
that's unnatural.
I'm not gonna lie, this is actually easy.
Rationally, they're not making it.
I know. I wanted to.
Make it a 5.
Oh, let me go back. Yes. Okay, this is what I wanted to show you. Look at this. Okay, now this one looks like there's a what in it?
Cubic function.
Yes. What would the range be of this?
Yes.
All real numbers.
All our numbers, because see how this part alone is going all the way up and then all the way down to negative infinity? If you had to, oh, let me go back here. If you had to do the domain and range for this guy, you'd have 2 separate parts. So you'd have one part where everything is above the lowest point, and then one where everything is really this is your function that you have. Everything would be above this y value, the 1.866, and everything is below this y value. And that's something that you'll investigate more when you're in pre-calculus. Were you asked me something?
Huh?
Were you asked me something?
Oh no, I was just stretching.
Oh. All right, so let's finish our graph here. Okay, so we had some good points that we had in between here. Remember, this is going to curve, and it will never cross your vertical asymptote. Okay, so that is one thing that I'll be picky on, is that it's not crossing there. And then you can pick out just some points from your graphing calculator to help you form each branch. And this one we had something close to like 2 here, but that's going to be in these bounds. Okay, and then for C, when you factor this right away, like if you factor the GCF out, okay, and then you're doing your zeros, if you were to do your zeros with the 4 times x minus 3, this would just be 4 equals 0, which you can't solve. So you would only have the x equals 3 or the 0.30 on your radar there. Okay, and then for the vertical asymptote, you're gonna do the zeros of the denominator, which is just x equals 1. And then the horizontal now, this is when the degrees are equal. So if the degrees are equal, the leading coefficient of the numerator is what? 4. The leading coefficient of the denominator is 1. Do not leave this as 4 over 1. What is 4 divided by 1? 4. Okay, so then this is going to be your horizontal asymptote. Okay, and then I want you to graph this. I did that quick because I thought that was the first thing that you did for those two, right? When you're putting in your these in, so here's 4 and then here's 1. If you were to do the 4 all the way up here, is that going to give you room to see the other branch? If it's already at the top there? Probably not. So instead, I'm going to scale by 4s. So this would be 4, 8, 12, 16. Okay, and I'm only going to do that for the y-axis. You're not happy with that decision?
Oh no, I'm just tired.
Oh.
Started.
And then x equals 1. All right, so whenever you have the cross, the T, okay, that is going to be one of the 2 branches. Actually, I'm going to show you. This one I actually scaled by 3s. I'm just going to show it to you on here. So you have, again, those opposite quadrants. And then if I wrote the homework up there,